Okay. Um, so, what? That's what I just did. Yeah, just now. Yeah. Thanks for checking. Okay. Oh, okay. Now we have more attendance. Good. Um, wow, he really went over this time. Okay. Um, so, so here for the homework, I'm separating questions by assignment. So we've already gotten the first question on homework 6. Um, now, I'm going to preemptively um, point something out about one of the first explorations in homework 3, just because um, there's a little bit of linear algebra involved, and um, it's possible that some of you may not have taken that. So I just want to make sure that doesn't. Again, there's very little. Really, it's the second semester that is much more linear algebra-y. And I'm also I'm trying something a little different here in class. So I found this program that I took it first for a spin, and it seems to work pretty well because on the one hand, I could type equations very quickly if I'm doing it in MATLAB, except that it doesn't show up in proper mathematical notation. It's harder to read. But what this does is, if I'm typing the equations in LaTeX notation down here, the lower left corner of the screen, then it processes immediately and shows up here as I type. So, of course, that'll also mean that whatever I put here mathematically will be legible. And I could do this, so hopefully it's a compromise between the various other things, or the writing on the board, which is less practical or maybe impractical in this room. So I'll try this out, and if it seems to be too cumbersome, then I just won't continue using it. But also, I haven't paid for this program yet. It's not cheap either, even before I convert to euros. Okay, so um, and what I'll do, of course, is after class, whatever I type in here, I'll post a final PDF. Okay, so so about homework 3, one of the first explorations. Okay, let's see if I can make this a little bigger. Yeah, it should be made a little bigger. Okay. Whoops. Zoom in a little more. Okay. Now, what this asks for is writing a system of equations in matrix vector form. And what I mean by that is I'll do an example. Dang it. Okay. So if I write out a system of equations, I'll just do 2 equations. So as I finish each equation, it'll show up on the screen. Okay. So for instance, ax plus, actually I'd like to make this bigger still. Okay. Ax plus by equals, let's say, u. And then for the second equation, let's say cx plus dy equals v. And so in this case, the unknowns are x and y. Let's put that in math mode. And then the right hand right-hand side values are u and v, and then the coefficient matrix entries would be everything else that you see here in a system of equations, A, B, C, D. So in matrix vector form, how I would write out the same system of equations is as follows. Okay. It's looking a little screwy just because I'm in the middle of typing an equation. Okay. So we'd have the coefficients from a first equation. Hello? What? Oh, I see what I did. Okay. A and B, and then in the coefficients from the second equation in the second row, C and D. So that's the coefficient matrix of a system. And then we'd have vectors for everything else. Don't crash them. Don't do this. Don't do it. Don't be a jerk. I haven't saved this file yet. That's going to really tick me off. Of course, it didn't happen when I was trying it out. Wouldn't this figure? Taking a picture of this just in case. Come on. Hello. I think I managed to confuse it. Okay. All right. While this is happening, I think I know how I can salvage most of this. I think I'm going to have to kill this program and restart it. Okay, because the actual file is here. Okay, good. I have all this. Or, no, I have almost all of it, of course. Okay. Section. Okay. Bye. Okay. Sorry about this. Okay. Okay, much of what I have is still there. So let's see if I can avoid confusing it again. Okay. Stop it. Okay. And of course, I should remember, like in anything else, save early, save often. Okay. But I think I'm going to be giving a healthy dose of feedback to whoever wrote this dang thing. Okay. It's going to do this again to me, isn't it? Oh, wow. I'm so pissed right now. I'm typing the exact same thing. and it wants to crash. Wow. Because what I did after class last time is search for what do you call a WYSIWYG LaTeX editor. By WYSIWYG, I mean what you see is what you get. You know, something like this, where I could just go ahead and. So apparently, I have an idea of what causes this thing to have issues. I'm going to give it one more chance, and then I don't know. Maybe we'll just cancel class or something. I'm kidding, but I'm that miffed. Okay. So I'm going to create 3 matching sets of brackets because I need a matrix for AX, A, B, C, D, a vector for X, Y, and a vector for U and V. So I'm just going to put that stuff in first. So at least then something shows up. And then what I can do is put things in between. Okay. All right. Save. And then now I can. So the unknowns are X and Y. And voila, there it is. Can you believe it? 3rd time's the charm. And then same thing for right-hand side. All right, so same system in matrix vector form. That's what I'm looking for in 611. In that time, I could have done the exercise 10 times over. And yeah, 15 minutes gone. Fantastic. So the coefficients, so the unknowns in the problem are the A's, A0, A1, the coefficients of a polynomial we're looking for. And then, so what's multiplying those in each equation, those are the entries of a matrix. And it's a matrix that's of interest. And then the right-hand side, of course, goes in the right-hand side vector, save. So you may not be used to this if you haven't had linear algebra or if you took linear algebra a while ago and then forgot it all. So that only, again, it only plays a limited role in this class, but this is just what I have in mind. Just writing a system down in this form, because the idea is when you are representing your interpolating polynomial in the most instinctively most normal way possible, power form, then you get the matrix that you get here is I defined earlier as a van der Waals matrix, and that's difficult to work with. But if you choose a different form of a polynomial, you can have a very simple matrix where most of the entries are 0. And both the Lagrange and Newton form lead to matrices that have that property, a lot of 0 entries. Because then that makes this whole system of equations for the coefficients of your polynomial a whole lot easier to solve. You can solve it much more efficiently. So instead of, for a degree n polynomial, needing on the order of n cubed arithmetic operations to get to coefficients, only n squared would be necessary at most. Okay. Now, are there any homework questions out there about any assignment? Yes. Yes. Okay. Okay. So about that particular. Yeah. Oh, like in the exercises section. Okay. There isn't really a close relationship between these two phenomena, except that in those two exercises, you have functions for whatever it is you're trying to compute, and it's just that in the conditions that bring about catastrophic cancellation, where the numbers are close to each other, then those functions that represent what you're trying to compute, x minus y, or the natural log in the other one, happen to have a large condition number. So you think of it as another way of explaining why these operations are problematic. That no, it's awful. Yeah, we hate large condition numbers.
Oh wait, I'm sorry.
Okay, yeah. So, okay, so in other words, when you were working these out, you were getting a large condition number. Good. All right. Oh, one is not considered a large condition number. Like something that can get arbitrarily large, like as close to infinity as you want. Yeah. Okay, so and this is I think it was relative condition number. Yeah, so it has to be that one because it may not even work with absolute. But as far as the function that you're dealing with, you could either work with. Okay, I'm gonna put this in here. Okay, so for condition number, this is exercises 1 and 2. I recommend using for a condition number using either x f prime of x over f of x. So this method of estimating the condition number could also use this. It would work anyway. Could also use the definition, just the difference in forward error divided by difference in backward error. But I think it'd be cleaner if you use this form. Is that what you're using? Okay. So what you should get is and basically they're treating this as y being fixed, and then x is a one and only variable, and it's just a matter of whatever you get for a condition number, if x happens to be close to y, it should be able to go to infinity. Yeah, so maybe just a little mistake in there. That if that's not what you're getting. Right. Any other? Floor still open? Yes. Oh.
I was just asking if that was for exercise 2.
1 and 2. It's the same kind of thing going on with different functions. Oh, yeah, Jesse.
So, going back to the first one you talked about today,
yeah.
Are you opposed to us setting it equal to 0 first?
Of this? Why would you? Okay. No, it's just because the system of equations, that seems strange, because the system of equations is the left side represents the value of your polynomial at each x value, and then the right-hand side is the corresponding y value. Now, I guess or do you mean like you're moving everything onto one side? Okay. I guess it doesn't really matter because these y values, they don't involve the unknowns at all. And really the problem is asking about this. So however you want to write the rest of it, doesn't really affect the problem.
Okay. And then in 613,
Okay.
it's asking us to prove that P sub n of x is equal to Q sub n of x. But it already told us that like P sub n of xi is equal to Q again.
Okay, this is 613.
Correct.
Okay.
So I was kind of confused at what it's asking.
Well, I wouldn't put it past me to mess that up. Okay. Okay, thankfully I did not mess up, except maybe in making this clear. Okay. So it's not wrong, it's just... Okay. Partially relieved. Okay, now the thing is, what this is saying is the polynomials are equal at these specific points, the xi's. But from this statement alone, we don't necessarily know that these polynomials are equal at other x's. Just like, for instance, if I have two parabolas, I can make those match at... I can come up with two parabolas that are equal at two given x values, but not three. So the degrees of these are degree n, and the number of points at which they match is key here. In terms of, if you have a polynomial with a certain degree, how many roots can it possibly have? So if you look at the difference between P and Q. So P minus Q is also a polynomial of degree at most n. Think in terms of its roots. Any other? Okay. Hold on. Oh. Okay.
I can see what the largest and smallest ones would be. I mean, I think we did that in class.
Okay.
I'm just not understanding. Like the last question, I'm not understanding what the degree.
Oh, okay. All right. Okay, in terms of you have a smallest exponent, largest exponent, and bless you, and also the precision. Okay. All right. So the way I've come up with this floating point system, the one that's given in the table, is for the exponent range and the precision, is if you allocate the same amount of storage for each part of a floating point number, sign bit, one bit for the sign, 11 bits for the exponent, 52 bits for the mantissa. Then this is what you would get. Now, okay. But what you find is that the actual range of allowable exponents, for example, is not this. Now, if you look at the one of the lectures I gave on computer arithmetic, where I was playing around with these things in MATLAB. Okay, actually, I'm going to take a peek at past diaries from around that time. I'm not going to tell. What?
I think it was the 28th.
Okay. Yeah. It was, oh, wait, September 28th?
Oh, I was talking about when you did the demonstration when you showed the powers
Oh, okay. Okay. Well, actually, I'll go ahead and take a look at that diary. Although, right at this point, I'm not going to tell you what I'm looking for. But okay. I'm feeling it's not this one. But it would have to have been from around this time. Dang it. Okay. Okay, that's all the previous stuff on error analysis. Okay, this is bugging me. Okay. All right, if I go back here, okay. This would be the most likely one. Okay. Actually, yeah, this is what I'm looking for. Okay. Now, see if I can make this. Yeah, I can make this a little bigger. So, what I suggest you do is, so what we have here are okay, representations of plus infinity, 1 over 0, negative infinity, minus 1 over 0, and then not a number, 0 over 0, because that is an indeterminate form. It could be finite, it could be infinite, we just have no idea. And so what I would suggest you do to see why the discrepancy, where that lies, is if you take these hex formats, because from other problems you've seen how we can decipher this. Now, of course, the first bit being a signed bit, and then the mantissa is entirely 0 in almost all of these cases. Well, this 8 here means a leading digit of 1. So you can see, like, what, if you look at this part and set aside the first bit, because that's a signed bit, what exponent is represented in these cases? And the other thing is, okay, so and this is the diary from, want to be completely sure. Yeah, the diary from this lecture from September 7th. And the other thing is, I want to point out about this particular floating point system I described in the table. This floating point system, assumes normalized numbers. That's what would lead to this value of the underflow level. But that is not the underflow level of IEEE. And the reason why is you have what's called gradual underflow. But you have, for particularly small numbers, it switches from the usual normalized mode to denormalized. And how is that reflected in the exponent? And to give you an idea about that, I'll flip over to MATLAB here. real min is actually that'd be 2 to the minus. Oh, you schmucks. Okay. That's not the actual smallest real not positive number. That is. So 2 minus 1074 is smallest positive real number. Now, let's look at that again in format hex. Okay, so that's what we have going on here. So what is the exponent in this case? As opposed to a number like, I'll pick a much larger, although it's still pretty small, like 2 to the minus 1020. I'm picking out one because that is that one would be represented using a normalized number. So here we have something very different in the exponent. So what is the exponent for this case, as opposed to the exponent really would be minus 1020 in this case? Because an exponent like minus 1074 cannot come about from the range of exponents that are stored in these 11 bits. Because 11 bits can only hold these. So that's another thing to look at as to why the actual floating point system you're using in MATLAB at IEEE does not quite agree with this, even though the number of bits allocated for each piece are exactly the same. But it has to do with normalized versus denormalized numbers. And also how infinity and NaN are represented. Any other? On homework 2 or homework 3? Okay. All right. Now, if I can get this dang thing to not crash again. Now, everything that I've been showing you with polynomial interpolation, we're actually going to put to use now. Okay. Figures I went on to the previous page. And now I got to find my place again. Okay. Now, as you guys benefited from considerably in Cal 1 and 2, polynomials are by far the easiest functions to integrate and differentiate. And of course, polynomials are. I'm going to make this. I don't like having things split across pages, so I'm going to put this onto a new page. Okay. So this is one nice thing about these functions. Also, easiest functions for a computer to work with, because to evaluate them or do anything with them, you just use the 4 basic arithmetic operations. Unlike functions such as sines, cosines, because sines and cosines are also easy to differentiate and integrate. But what about evaluation? You have to settle for an approximation beyond just round-off error. You always have round-off error to deal with. But with functions like sine and cosine, or like, say, e to the x, you have something extra on top of that to introduce error. So less error to consider. Really, it's only round-off error that's a problem, which, as we've seen in some examples, can still be substantial, but this is the best that we can do. So throughout this chapter, oops. One of the difficulties with this is I'm typing down here, and it's a little small for me to see. And I don't know if I can make that bigger. I'm not sure if I want to either. So how it's going to work throughout this chapter, the overriding theme. Okay. So for performing whatever calculus operation, whether in Cal 1 land of derivatives or Cal 2 land of integrals, is you approximate your function f of x by a polynomial. Whatever function you're trying to differentiate or integrate. And the way we're going to do that is using the interpolation techniques that we were just dealing with. Generally, we use Lagrange interpolation. For this purpose, it is a bit more convenient. Even though in other applications, Newton interpolation is best. And once we have a polynomial, solve whatever problem, and by that I mean computing f prime at x naught, or computing the definite integral of f on some given interval ab, because for whatever polynomial you're using to approximate f, you can go ahead and solve a problem exactly. So we're going to design methods. You can see how methods can be designed for computing approximate derivatives, approximate integrals, all based on polynomial interpolation. But even if by limiting ourselves to that, there's still a lot of variability involved into how we actually proceed that have advantages or disadvantages for different situations, different functions, etc. So all I'm starting with today is numerical differentiation. That's the theme for this week. I'll barely scratch the surface of numerical integration on Tuesday, and then we have fall break. Okay. So now we've seen some examples on how to approximate derivatives. This came up in homework 2. For approximating derivative, okay. Just a little typo here. Okay. So we saw this. This was in exploration like 2.13 or something like that. Oh, no, 2.1 is where it was. Another one was using f of x naught plus h minus f of x naught minus h over 2h. So, so these formulas, I'm going to give them names. The first one is called a forward difference. And the second one is called a center difference. Because this first formula only uses information at x naught or to the right of x naught. We're assuming that h is positive. Okay. Whereas this one, we want the derivative at x naught, but we use a point to the right of x naught and another point to the left of x naught. And x naught is exactly in the middle. And that's why it's called the center difference. Another related formula, if we take the forward difference and just replace h by minus h throughout, okay. So then we have f of x naught minus f of x naught minus h. So we're using only information to the left, there's a backward from x naught. That is called the backward difference. Okay. Another formula that we saw, this was worked out in an example for a second derivative. And here we use, again, same function values, f of x naught plus h and I need to include one more term here. As I try this out, I'm figuring out slowly but surely how best to type out these expressions so that more things show up on the screen sooner. But it's something, admittedly, I need more practice with. Okay, now, and we've seen how to derive all of these using Taylor series. Now, okay, I need to close this equation here. All right, so what we do is we do Taylor expansion of whatever points you're evaluating f at, besides f x naught itself. So x naught always serves as a center of your Taylor expansion. Now, the way these worked out, you actually worked out the two up here in the second homework. This one was done as an example in that same section. I'm going to show you another one just for so you can see a different example. Okay. So what I want is to approximate f prime x naught using values at 3 points, x naught plus h, and x naught minus h. Because in all of these for first derivative, we use only 2 points. Also, sometimes what happens is you have your function defined at certain points, and you want a derivative like at the leftmost, whoops, not minus h, I already have that one, plus 2h. These are 3 points I want to use. So I suppose I don't have any information about f of x. Okay, this is one thing I've grown to already hate about this program. That sometimes I'll type in $sign to say I want math mode, and it thinks I want an actual $sign. Okay. And I have no way of easily telling it no. So if we don't have any information about f for x less than x naught, like if we can't get the value of x naught minus h, because maybe you only have values of f at specific points, and you want a derivative at the leftmost boundary of whatever domain you're working with, then you need something like this. Now you could use a forward difference. But we want higher accuracy, second order accuracy. Meaning the error is big O of h squared. Because what happens is, and as we saw in the homework, the forward difference, backward difference also, just because it's so similar to a forward difference, these are first order accurate. In other words, the error term is big O of h. In other words, it's proportional to h. So for example, if you decrease h by a factor of 10, the error decreases by a factor of roughly 10. But the center difference is second order accurate. So the error is big O of h squared. So if you decrease h by a factor of 10, the error decreases by a factor of 100. But if you use enough points, you can get as high an order of accuracy as you want. But then there's more expense in evaluating them. So if I only have information about f at x naught and also to the right of x naught, I can use this and get first order accuracy, but I want second order. So that means I need another point. I need these 3 points to get that job done. So here's what I'll do. I need to Taylor expand f at evaluating at these 2 points centered at x naught. Okay. No, I do not want question marks. What are you doing? Yep, not a fan of this program. I mean, it's technically doing what I want it to do, but man, the bugs. Bad coding. So here are my Taylor expansions. So first for f of x naught at plus h. All right, so f x naught plus, and you've seen this before. Okay, plus 1/2 h squared f double prime at x naught. And then, let's see, I'll go out one term more. If you go out too far, you can always cut back later. It's better to go out too far than not far enough. 1 over 3 factorial, which is 1/6 h cubed f triple prime at some unknown point. So this is my remainder term. So I'll evaluate it like C1. I'm calling it C1 because I'm going to have 2 Taylor expansions. Okay, so now I'm going to just copy and paste this one. Something I often wish I could do if I was working at the board, but can't. So if I replace h with 2h, I just have to adjust these. So I have 2h, and then I have, instead of 2h, so I'm going to have 4h squared over 2, and then I'm going to have 8h cubed over 3 factorial. Okay, so now the thing is, I have my Taylor expansions. I also have just plain old f of x naught. So the form, okay, of my approximation is f prime of x naught is approximated by some coefficient, which I'll call a0, times f of x naught, plus another coefficient a1, fx1, plus another coefficient, not x1, x naught plus h, and then another coefficient a2, f of x naught plus 2h. So I have these unknown coefficients, a0, a1, a2, and I need to solve for these. So in order to figure out what values of these coefficients will give me the derivative, and also cause anything I don't want to cancel, I need to use these 2 Taylor expansions. So what I'll do at this point is I'll substitute in the expansions. So what I'll have is f prime at x naught. Actually, I'm going to need a multi-line equation. Okay. Okay. And what I'll do is I'll have a naught f of x naught. That's not going to change at all. Plus a1 times, and I need to dump this Taylor expansion in here. So I'll go ahead and copy that. and put it in. And then, let's go down to the next line here and take the other expansion and dump that down below. Okay, so now I have everything substituted in. And I'm going to cause this to go onto a new page. Okay, before I do anything else, any questions about how we got to this point? Actually, can anyone spot my one mistake that I just spotted? C2. I heard someone whisper that, I think. Yeah, the unknown points in your Taylor expansions are different. So this is one of the drawbacks of copy and paste, that not making all the necessary changes. So all I did was I prescribed that this is a form of my approximation. I'm using these three function values to approximate the derivative as best I can. Taylor expand these two, dump the expansions in here. And now what I'll do is rearrange this to combine like terms in the sense of like f of x naught, I'm going to group those together. F prime, I'm going to group those together, and so forth. So what I have is a0 plus a1 plus a2 times f of x naught. And then what's multiplying f prime? I have a1 times h plus a2 times 2h. All that's multiplying f prime. And what's multiplying f double prime? I'm going to simplify these. I have a1 1/2 h squared plus a2 times 4h squared over 2. So a2 times 2h squared. I don't want a subscript there. F double prime x naught. So I have these combinations of coefficients. Now, and then what's left is, okay, my remainder terms. So I have, okay, a1, and then the remainder term from the first expansion. Whoa, that went very badly. Okay. Let's try that again. A1, yep, plus the first remainder plus A2 times the second remainder. And that would be right here. No. This thing is not listening to me. Okay. Oh. Okay, paste in the wrong place. There we go. All right. So now we're in a position to impose some conditions on A0, A1, and A2. First of all, we want this to equal f prime of x naught. So any other terms, if possible, we want to make disappear. So anything multiplying f of x naught must be 0. So I'm going to write out a system of linear equations. So we must have a0 plus a1 plus a2 must be 0 to make this term go away. Now, can anyone tell me what another equation is based on what we see up here? since we want all of this as much as possible to collapse to f prime of x naught. So I've imposed this. This has to be equal to 0. What else should I impose? A1h plus A2 2h. What should it equal? 1, yes. Because that term we actually want. We want this to just equal f prime x naught. Okay, give me another. Yeah, this part must be 0. Now, the convenient thing about this is because this must be equal to 0, if there's anything I can factor out, I can. So I can actually drop the h squared. I mean, it doesn't really matter whether you include it or not, but just to reduce clutter. So a1 times a half plus 8 plus 2a2 has to equal 0. So now the thing is, I cannot go any further. I have 3 unknowns, I have 3 equations. Anything else will cause the system to be overdetermined. So in other words, this part, I cannot make that go away. This is where my error is going to come from. So what I'm going to have here is, this is my exact value, this is what I want, f prime x naught. This is going to be, so my approximation is going to come from a0, a1, and a2, and then we're going to have something left over. That's going to be the error term. And once we have values for a1 and a2, then we can get an idea of what that error is supposed to be. Okay. Or really, it's the left side that's the approximation. What we're going to get over here is f prime plus this stuff. So really, what we're going to have here is like minus the error. But really, it's the magnitude of error we care about more. All right, so now we need to solve a system of equations. Now, these two equations, the last two, do not involve a0. That helps. So really, the last two equations we can solve those. And then to make it a little more convenient, I'm going to divide the second equation by h. Okay. And that's 2a2. So I'm just going to move the h to the other side. Okay. All right. Now, okay. And then the other thing I'm going to do is I'm going to take the third equation. I'm going to multiply through it by 2. Yeah, because I don't like fractions. So if I multiply by 2, that 1/2 goes away. And then this becomes a 4. Okay. All right. So for instance, what we could do is like along the lines of Gauss elimination, if you will, but or just to save time, you can go ahead and try to solve the system on your own time. I can tell you what the solution is. So because honestly, I do not trust myself to do algebra correctly when I'm up here. Sad, I know, but I told you what happens to my IQ when I'm up here. So there is a unique solution, and what we get is so a1 is equal to 4, 4 over h rather, or no, it's I can write it as 4 over 2h. I'll use a display equation for this. And it seems like, well, you're wondering why I'm not writing this in lowest terms. You'll see why. A1, to satisfy the third equation, is equal to minus 1 over 2h. So that way, sorry, that should be, I have these indices backwards. That's A2, and that is A1. Okay. Because now if I take this and multiply it by 4, and then it cancels with this. And then the first equation gives you means that all the coefficients must sum to 0, which is always true of these kind of differentiation rules. So a0 equals minus 3 over 2h. This is why I wrote this as 4 over 2h. This way they all have the same denominator. It's just that these two are already in lowest terms, so I can leave this one not in lowest terms. So what we get for approximation is f prime and x naught equals, so we get minus 3 f of x naught plus 4 f of x naught plus h minus f of x naught plus 2h all over 2h. So that's the approximation of a derivative. And then what we have is if I take a1 and a2 and plug them in here, so a1 is 2 over h. So because a1 and a2 have a 1 over h in them, I'm going to get h squared in these terms. So in other words, the error is going to be of order h squared. So I'm going to have minus, okay, so I'm going to have 2 over h. I'm going to cheat a little bit. And then I have 1/6 because of a 3 factorial, h cubed. So if I put these all together, so I'm going to have 1/3. Okay. H squared, and then we have f triple prime c1. No, I want an actual backslash. Why are you doing that? Quit being a butt. God, this is aggravating. Okay. And then I have the other error term that comes over here, a2. a2 is okay, minus 1 over 2h, but I have to, and then I have 1/6, and then I have 8. So I have 8/12, so that's plus 2/3. 2/3 h squared f triple prime at the other unknown point, c2. Okay, so what I have here is second order accurate because the error is of order big O of h squared. Now, if I had chosen to use more points, I could make it even more accurate, order h cubed, order h to the fourth, etc. There's an exploration where you look for a fourth order accurate approximation of the first derivative using specified points. Now, in the previous examples, I've been able to combine these into one using what theorem from Cal 1? Somebody? Intermediate value theorem. I think I heard somebody say that. As I've told you, my hearing sucks. I cannot use that here. And the reason is these terms are of different signs. So the coefficients. So when the coefficients are all the same sign, you can treat this like some sort of average and condense it into one thing. But not this time. So actually, we're not able to get a condensed error term using Taylor series. It's one of the drawbacks about them. But later when I talk about using Lagrange interpolation to derive these same kinds of rules, we will be able to take care of this much more easily. But it's more of a pain. And actually something that I found that other numerical analysis textbooks have kind of dodged. Like, they don't even talk about this. They're such wusses. Okay, I'm trash talking my marketplace competition. But anyway, that just was kind of disappointing. Okay, so but we've seen here how you can use Taylor series. I'm running low on time here. So what we've seen here is can use Taylor series expansions of f of a point at which you want a derivative x naught plus IH. Where I is an integer. So we assume that the data is given in terms of equally spaced points. Although that's not really essential. When you have non-equally spaced data, you can still use a similar approach. It's that your formulas aren't quite as clean. To obtain a system of linear equations for coefficients of an approximation of f prime x naught. Now that's what I've demonstrated here today, but we've seen how the same idea can be used for a second derivative. So that's in section 2.1. Again, you're combining. It's just that you want a different term to stick around. So of course, the more points you use, the more of a pain it is to solve a system of linear equations. You may enlist the help of MATLAB or other software to do that. So the general form is the following. Okay. Whoops, I have a dollar sign down here. So f jth derivative at x naught is approximately a sum over, say, n plus 1 points of, so you have coefficients, which I'll call AI, and you're evaluating f at these points. You're using Taylor expansions of these points to approximate your derivative. In general, the order of accuracy is h to the p, where p equals, and in my mentally hobbled state, I will try to work this out on the fly. So p is equal to, so the number of points that you're going to use as a start. So we have n plus 1 points minus, okay, so for instance, okay, all right, so if j is the order of derivative that you want, okay. Now, so that's what, so in general, that's the order of accuracy. How many points you use, n plus 1, minus the order derivative you're taking. Now, I want to point out, though, it can be higher due to symmetry. And an example of that is this approximation of a second derivative that I have up here. We have 3 points, so n is equal to 2, because it's n plus 1 points. And then you subtract off 2 because you want second derivative. That would suggest that this rule is first order accurate, but it's actually second order accurate. So if there's some nice cancellation due to using standard differences, you can get a higher order of accuracy, maybe at most 1 higher, but that's about it. Okay. Now the last point I want to make is a segue into what I'll talk about on Thursday. The error term involves a higher order derivative. And what that means is, so the approximation is exact if f is a polynomial of, sufficiently low degree. So for example, here, the error involves a third derivative. So this approximation is exact for any polynomial up to degree 2. So really degree n or less, where n is the number of points that you're using. So what does that mean? It actually describes a connection between what I've shown you here of Taylor series and polynomial interpolation. So what we can say is our approximation of f prime, or whatever derivative you want, I'll just use f prime in this case, is the exact derivative of Pn, the interpolating polynomial, or so polynomial that interpolates f at all these points that we're using in our approximation up here. Okay, I know that I'm at the 0 minute here, 0 minutes left. So, in other words, the approximate solution is the exact solution of a nearby problem. In other words, we want the derivative of f. We approximate the derivative of f by computing the exact derivative of a function near f. In other words, a polynomial interpolant. Now, this notion of the approximate solution being the exact solution of a nearby problem, that led to, so what concept from when we talked about error analysis, what did that lead to? We use that to define what kind of error. We've only seen a few different kinds of error in this class, so backwards specifically. So in other words, the polynomial interpolation error is a backward error. Now, when we learn more about how to compute the error in our derivative approximations, and we know how to compute polynomial interpolation error, because that was covered in the previous chapter, what relates the two errors? Forward and backward error, what relates them? Condition number. So this allows us to compute the condition number of numerical differentiation. And that's something we'll do later. And so we get an idea of, is this a well-conditioned or ill-conditioned problem? Because we'll have both formulas for both kinds of error. So the ratio will give us an idea of a conditioning. Okay, sorry for going 2 minutes past time. And I guess some of you have probability in 3 minutes. So, okay. Math never stops, does it? Okay, so till Thursday.